All right, so what we're going to look at a little bit here today is more on differential equations. So in general, and what we're going to deal with is types of equations that follow along with what we've defined right here, non-homogeneous differential equations with constant coefficients. So a couple of definitions. The constant coefficients basically refer to these multipliers here on each of the derivative terms. All right, we're going to assume each of those to be constant. That's normal when you're dealing with, let's say, RLC circuits or the types of things that you guys are used to dealing with in your classes. So we're not going to touch anything where it's time varying. That gets a little bit more complicated. Now, what I notice is that in my sort of general view of the world, what I always have on this side, where I have the derivatives, I have my y of t, which is my output. All right, when I say an output, what that means is if I had a circuit, let's say an RC circuit, x of t over here would be my input, and maybe the voltage across that capacitor would be y of t. So y of t is always my output, x of t is always my input, and in the context of math, we typically call this guy a driving function or a driving force. And I can always separate this equation such that I have the output terms on one side and the input terms on the other. Okay? All right, and we're going to work on trying to get our equations in that form. Now there's two general types of these equations, right? We call them non-homogeneous and homogeneous. Okay? Ones that have a driving force, in other words, where the differential equation like I have here on the left is equal to something, that's what I would call a non-homogeneous term. All right, where there's some kind of driving force that's on the right side. A homogeneous equation is one that does not have a driving force. This guy here, the homogeneous equation, gives rise to the transient response. All right, so the transient response, basically what this is saying is I can get a transient response even if I don't have a driving force, right? Which kind of makes sense because if you think about it, if I had a capacitor over here that was charged and I did not have a source, let's say there was no source in this system, there would still be a response arising from the differential equation even with no input. Okay? So that's, essentially that comes from the fact that this guy is charged up and he's going to discharge over time. So the homogeneous is basically a situation where I have the differential equation equal to 0 and it gives me the transient response. Non-homogeneous is where I have the input present. There is a homogeneous equation associated with each non-homogeneous equation, and that associated equation basically just takes the original equation and sets it equal to 0. Okay? So in other words, the way we looked at this in class the other day is I said I could think of this whole thing as x of t plus 0, having two different types of inputs. Solve it once to get the response to the actual driving function. Solve it again to get the response to 0. Okay? And I combine those two results. So when we're solving these things, that basically leads us to sort of a three-step process. The first is that I solve the homogeneous equation. In other words, I solve the differential equation equal to 0. Okay? The response here, the solution that I get, is called either the homogeneous, the transient, or the complementary solution. The book uses the term complementary. All right, so I will refer to it that way, y sub c. All right, and then also refers to so it uses the term complementary solution. So our first step is to solve the homogeneous equation, which is where the equation is equal to 0. Then we solve the non-homogeneous equation. The solution to this guy is called the particular solution. Okay. For this, we use something called the Undetermined Coefficients method. At least that's what I'm going to use. And I'm going to call that solution yp of t. Now, both of these solutions taken together, all right, must be added together to yield for me the total solution, which satisfies the initial conditions. Okay? So the important thing to remember is it's in step 3 where I finally bring in the initial conditions. In other words, I have to have both the particular solution and the complementary solution. So solving the homogeneous equation gives me the transient response. Solving the non-homogeneous equation gives me the particular solution or the steady state response. And putting them together gives me the total solution. In other words, the combination of the two, where we know that the transient response always, as t goes to infinity, it is always the case that this guy is going to disappear in any real system. Okay? Now I say in any real system. There's possibilities that I could have some theoretical situations where that wouldn't go away, but those don't really happen much in real life. All right, so what I want to do is follow along with what's in the book. So in section 7.3, okay. So in section 7.3, they introduce our first order differential equation. And I'm going to look at our first order differential equation of this form. So over here, again, these are my output terms. This guy here is my input term. And the book considers a couple of different input terms. I'm going to consider two of them here. All right, the first of them that I'm going to consider is, let's say x of t is equal to a unit step, a u of t, like that. All right, now, hopefully you guys have mostly seen the unit step function before, but I'm going to define it here real quick. The unit step function is a function that is 0 before time t less than 0 and is 1 for time t greater than or equal to 0. So there's a discontinuity that happens right here where this guy sort of shoots up. All right. We use the unit step function all the time in engineering analysis to refer to things that are basically 0 before time t equal to 0 and then change after the fact. So that kind of, if you think about what am I using the unit step function to represent, if I had a circuit, for instance, and I had this type of condition here, if I close this switch at time t equal to 0, right, closing that switch would represent all of a sudden a voltage at the terminals Vin going from 0 to whatever this value is. Let's say that value was 1 volt, right? So the act of closing the switch, I can model that as basically a u of t like that. So instead of having this switch and source combination, I could have this one source modeled as u of t. So we use that oftentimes in a mathematical context to be able to represent sort of the complete situation in a way that's easier to capture mathematically. Okay? So imagine that's the type of problem I'm going to first try to solve. So I'm going to say I've got a situation where I've got dy by dt plus a y equals a u of t. All right, so if you look at a situation like that one, in this particular case, if I were to write a differential equation that said, okay, well, if I wanted to figure out V out, and I had V in here was equal to U of t, if I were to write the differential equation for this, you guys should be able to write it. It basically would become dV out by dt plus 1 over RC V out equal to V in over RC, or U of t over RC. Right, so you guys should be able to sort of write out that specific differential equation without too much difficulty. But what I can see is the output in this case, my y of t, if you will, is the voltage across the capacitor. My input is this input source. So again, I say that only because what we have on the left side, the derivative side of the equation, is always where my output is. And that's some term, a current or a voltage that I'm trying to find in the circuit. The input side is always the sources that are connected to it. All right, so I'm going to do this in a purely mathematical context. Okay, so I said here's my equation. What I've done is I've said I've got an input, which is basically a constant multiplied by this step function, and I'm trying to find my output. So I said I had 3 steps. So step 1, I said, was to solve the homogeneous equation. Okay, so the homogeneous equation, dy by dt plus ay equals a, and or equals 0, sorry. That's the homogeneous equation. The homogeneous equation is equal to 0. So for this, I guess a solution. Now, I could guess y equal to 0, all right, but that's kind of a trivial guess. We know that there has to be a transient response, and we have to capture that. So what we do is we go ahead and we guess y of t, and I'll call it y sub c. I guess, in particular, if I want to write it this way, I can say that the equation should be written really in terms of y sub c. So y sub c is equal to, I'm going to guess, not a, because I've already got a. I'm going to guess that that guy is c e to the negative, or e to the st. So y sub c is equal to c e to the st, where I know that c is a constant that is never equal to 0. Because if I had, then it was equal to, then this whole equation here would be equal to 0. All right, so we always guess that when we're solving the homogeneous. So what do? I plug that in now to this equation, and I get d by dt of c e to the st plus a, okay, I'm just taking the derivative of that term, plus a times c est equal to 0. So I take the derivative, and I get s c e to the st plus a c e to the st equal to 0. Now I can factor out terms here, right? I can say that I have c times e to the st, s plus a, all equal to 0. Now I know that c is never equal to 0, and I know that e to the st is never equal to 0. So I know that s plus a must be equal to 0, right? I have a product of 3 things, 2 of which can never be 0. So the third of them better be 0. So I get s equals minus a. And so now I know that my complementary solution is equal to c e to the negative at. Okay? All right. So I have that down so far. But I'm not done. That was only step 1. Step 2 was to solve the homogeneous equation. Or sorry, solve the non-homogeneous. And for this, we go back to the original equation, dy dt plus ay equals a u of t. All right, now I'm only interested in solving this guy for the range over which he has an input. So if I go back to my unit step function, my unit step function is basically 0 before t equal to 0. So basically what I'm going to do is I'm going to solve, so for t greater than or equal to 0, I have that this equation is dy by dt plus ay equal to a. Okay? So essentially I'm just plugging in that definition. And I'm going to guess that my particular solution, I'm going to guess that that guy is equal to b, is equal to a constant. And what I'm going to do is I'm just going to plug that in and see what happens. So I have dyp by dt plus ayp equal to a. And I'm going to plug in my guess. Now, why did I pick a constant? I call this method the method of undetermined coefficients because what I have is one coefficient that I don't know. It's undetermined. I'm plugging it in. Why did I guess a constant? Well, solving the non-homogeneous equation is always solving for the steady state condition. And I know that if I have a circuit or some other kind of system that has reached steady state, I know that the voltages and currents should become constant. So I'm going to guess a constant. Okay, so if I have a circuit with DC sources, I guess I need to be clear about that. If I have a circuit with DC sources, then what I expect to have happen is if I wait long enough, my voltages and currents, which are my outputs, should become constant. So it makes sense to guess a constant. So I'm going to put in here my guess. Like that. Now because B is a constant, that becomes 0. So I have that A, B equals capital A, so that B must be equal to capital A over little a. Okay? Now, in a real problem, these would be numbers. Okay? And so if they were numbers, I would plug those numbers in. We'll do an example here in a little bit. All right? Now I have step 3, which is to combine yp and yc. So y of t equals yp plus yc. All right, so right now what I have is that y of t is equal to, so my complementary solution was c e to the negative at, and my particular solution was capital A over A, like that. And I should be careful because given the way this guy is defined, because nothing's happening, really I have a times u of t because nothing's ever happening before time t equal to 0. So that u of t is important, right? It defines that essentially this guy is equal to 0 before t equal to 0 and doesn't start doing anything until t equal to 0. All right, now I did give an initial condition here, so I should have back in my original system. Let's say my initial condition was, I guess y of 0 equal to, I'll just write it as yo. All right, so what I do is I say at t equal to 0, I have y of 0 equal to y0. That's got to be equal to c e to the negative a times 0. So that whole term becomes c, right? Because e to the 0 is 1, plus a over little a, like that. So I have that y0 equals c plus a over little a, or that c has to be equal to y0 minus a over little a. That gives me that the full total solution is simply y0 minus a over little a e to the negative at plus a over a, all of that times u of t. Okay? All right. Now, one thing I should be able to do is, I could do a check on this and see, well, what happens at time t equal to 0 and at time t equal to infinity? So as t approaches infinity. Okay. So as t approaches infinity, the exponential term goes to 0, and I get my steady state solution, a over little a. At time t equal to 0, right, I have y naught minus a over a plus a over a, which is equal to my initial condition, y naught, exactly what I expected. All right, this gets a little bit easier if I look at an example. So let's say I had dy by dt plus 5y equals 6, u of t. Okay, again, could represent something that a circuit is doing. So for my step 1, solve the homogeneous. All right, you guys should have done this many times before, so this isn't too particularly fancy for you. All right, so I set that equal to 0. Again, I would guess that y sub c equals c e to the st, with c not equal to 0. And you guys should know by now that means that I get this polynomial here, s plus 5 equal to 0. So s equals minus 5. So I get my y sub c is equal to some unknown constant times e to the negative 5t. All right. Now, step 2 is to solve the non-homogeneous, homogeneous. So I have dyp by dt plus 5yp equals 6 u of t. And again, I'll write this, so for t greater than or equal to 0, I have y dyp dt plus 5yp equals 6. So I got rid of the u of t. So I'm going to use that undetermined coefficients again. I know that if I have a constant source, that's likely to give rise to a constant output. So I'm going to say y sub p is equal to some constant b. So I'm going to say I have db by dt plus 5b equals 6, like that. And this term becomes 0, and I have 5b equals 6, where the b must be equal to 6/5. Okay? So now I'm on to step 3, which is to solve or find the total solution. Find total solution. Y of t equal y sub c plus yp. Again, because this guy had a source that turned on at t equal to 0, I need to multiply that all by u of t. All right, now again, I didn't give an initial condition, but let's say that I said that y of 0 was equal to 3, for sake of argument. All right, so my output was initially equal to 3. So if that's the case, let's combine everything. So y sub p, I said, was 6/5. And I have my y sub c was this guy, c e to the negative 5t. c e to the negative 5t. All right, all that times u of t. So at t equal to 0, y of 0 equals 3. Right, 3 is what I chose as my initial condition. Okay, so I say I have y of 0 equal to 3 equal to c e to the 0 plus 6/5, like that. So this guy becomes 3 equals c plus 6/5, or c equals 3 minus 6/5, which, if I want to put that as a number, and pull up my calculator, 3 minus 6/5 is equal to 1.8, like that. All right, so I have that y of t is equal to 1.8 e to the negative 5t plus 6/5 u of t. Okay, and that is my solution. All right, in the next video, we're going to look at a more complicated type of input. All right, but dealing with steps is generally pretty easy.